Recording in progress.
All right. So, uh, tonight we're going to be talking a little bit about something called the chi-square distribution. When we start looking at the chi-square distribution, it's some of the stuff that we do with it is probably going to come back to haunt all of you. Because if you remember all the way back in week number 2, when we're talking about different types of medical tests, some of the stuff that we were talking about way back then is also going to be or looks similar to some of the things that we're going to be doing today. With a chi-squared test, the general idea is we're going to be looking at what was observed versus what did we say expect to happen. And then based on our observations, based on what we expect to happen, we can ask an important question. Does there seem to be a difference between what we saw versus uh, what we were actually expecting? And I will say, with chi-square tests, the way that we're going to look at them, there's a lot of different things and a lot of different ways that we can really, really, really screw things up. For example, at one point I was interviewing for a position down at Wayne State University, uh, going to be working with some social scientists and dealing with recidivism rates and looking at it. Does there seem to be any association? Does there seem to be any way we can help people who are coming out of prison essentially not go back into prison? Uh, and the way that the data they were using was being analyzed, when I saw that, I was like, are you sure you really want to do it this way? And tried talking with them about why they were doing it the way that they were. And gonna be honest, the work that they are doing, if they come to the correct conclusions, if they do a really good job with what they're doing, we're going to be decreasing the recidivism rate for a lot of people. If you are say on the a right wing and you're like, we pay too much in taxes and that sort of thing, well, if we can reduce the recidivism rate, we could probably see a huge cost savings from sending people to prison. If you're on the left and you think that perhaps prison isn't always the best option, or uh, we need to do more to say keep former prisoners out of prison, which is also a very worthy goal. Um, the type of research that they're doing will actually uh, be relevant and useful for both type or for both groups of people. Unfortunately, the way that they were trying to do it and some of the things that they were doing, again, when I was looking at it and talking with them about it, uh, all I could hear was alarm bells ringing in my ears saying, are they sure they want to do it this way? Based on the way that they're doing it, can they find things that are useful and relevant? Maybe. Are they going to spend lots of money and potentially start making recommendations to, say, judges, uh, who, people that run prisons, people in state of Michigan, stuff like that, that could end up, say, backfiring and actually making things worse. Yeah. So, uh, when I went to analyze the data that they were using, I just kind of looked at one, if this is going to be the job that I do and this is what they're going to expect me to do all the time, I don't want this job. So, not going to get into the actual details of the types of things that they were doing, uh, but I will show you some of the calculations that are going on, and we will actually talk about a couple different times when, say, a chi-square test, like we're going to be talking about tonight, was used, but was not used quite as properly as it should have, and some of the consequences that came about from that. And depending on how much we get done, we might actually start talking about linear regression tonight. I hope so. If you look at the syllabus and compare where we're at versus what I have on the syllabus, you'll notice that we're like a week and a half behind. I'm not worried about it. We're already doing a lot more than we're supposed to be doing in here. So I'm not going to be in a mad frenzy to like finish up anything before we have, or before some of you have time to actually absorb what we're doing. But in the meantime, let's take a look at some of the stuff that I'm actually talking about here. So, shoot, sorry. It's been a while since I've used this particular camera. So I need to flip it over. Otherwise, everything's going to be upside down and backwards. And even seems like this camera doesn't necessarily want to focus. So my apologies for that. All right. So back in week number 2, as you will remember from all the nightmares that you have about it, we were dealing with data in a box that kind of looks like that. And we had, let's say you are positive and negative, and then well, we could have a test that's predicting that you are positive or you are negative. And again, this is a lot of the material that we talked about week number 2. And when we're when we were looking at all that data, I'm gonna try to do these calculations really quickly. So we looked at, say, we have 100,000 people, and let's say we know that 1% of all of those people have a, particular disease. So 100,000 people, what is 1% of 100,000? It's going to be 1,000 people. What percent of people are left over here? This is going to be 99% of the people. And because you all totally remember everything that went on with all of that medical testing stuff that we did, you know that whatever is in this box plus whatever I need to write here has to actually equal 100,000. So we have 99 or 99,000 people down here. And let's say we know that the false positive rate is equal to 0.05, or let's say 5%. Let's say the false negative rate is also going to be that 0.05, or the 5%. So when we're trying to fill out all of these tables here, what we're going to be doing is basically what's going on here is we know that 5% of the people that have the disease are going to test negative. So that's this false negative thing here, which means 95% of the people that have the disease are going to appear in this group. And again, the number here plus the number here has to total up. So I know I'm going to have 50. Over here, we need to do another quick calculation. And I'm actually going to bring up my graphing calculator real quick because I don't want to screw any of this stuff up. All right. So what's actually going to go on in here is going to be 5% of the 99,000 people that we were looking at. So 99,000, and I know you can't see what I'm putting on the calculator, uh, but it's all really boring stuff anyways. So I've got 4,950 people here, which means over here, I'm going to have 99,000 minus 4,950. So when I do that, so 99,000 times 0.95 if I wanted to. And I definitely want to do that here. There's 94,050 people in this group. Now I have to add all these things together. So 94,100 people over here. On the other side, 4,950 plus the 950 that we had up here. So we will have a total of 5,900 people in this particular group. So if I pulled up that exam one calculator thing, conditional probability calculator, put these numbers in, these are the numbers that would actually be appearing in the table. And if we look at the data the way that I've got it right now, uh, if we expect there to be 1% of the data, or 1% of people have whatever this disease is, and we believe that there's this 5% and this 5% going on here, everything that we get in here is what we would expect. Now, what we need to do is actually go out and look at uh, what is the observed number of people that are actually going to be in all four of these different groups. Again, assuming that we have a population, or we're going to be, say, testing this on, say, 100,000 people. And one of the weird things that can happen here is these are the values that we expect. But if we didn't know any better, we might look at these numbers and go, okay, someone calculated all these, and this is what we're actually seeing. And then we can go back and try to calculate what we expect. Now, some of the calculations that we have to do in order, or come up with in order to do that, uh, sorry, so with what we've got here, these are all values that we expect based on, say, theoretical calculations. What is the real thing actually going to look like? I have no idea. But let's say we're able to go back, or we run whatever test it is that we're looking at, and when we uh, get everything done, so this, and I'm making these numbers up, uh, but let's say, so I'm going to write out here, this is what we expect. Now, when we go and say, look at real data, so we're going to have test says positive, negative. Again, we're going to be looking at everything in here. So we're expecting to get 950. Let's say we actually get 1,100 people that are in this group. Well, let's say over here, we've actually got 20 people in this group. And then one of the things that we have to do with all of this is, again, add everything up for row totals, add everything up for what are called column totals. In this case, it's going to be 1,120 up here. So is this number of 1,120 different from the 1,000 that I was expecting up here? Yeah, yes, it is. Uh, but hopefully by now you realize that a lot of what we're doing, uh, the numbers are always going to be different. But the question we're asking is, does there seem to be a statistically significant difference between, say, what we expect, what we look at? So in this particular case, and I'm trying to do this all on the fly, which means there's a really good chance I'm going to screw something up. But we'll see. So 100,000 minus the 1,120. That means down here, I'm actually going to have 98,880. And going through all this, I'm going to try to make it easy on myself. I'm going to say I've got 95,000 there. Which means out here, going to have 3,880. Now I have to combine these together. 95,020 in this group, 3,880 plus the 1,100 up here, 4,980. And again, this is when you add these up, it should come out to be 100,000, just like we had before. So, in theory, or based on what we should be expecting, we believe that the values that we have up on the top here are going to be the what we should be seeing. But let's say we went to a couple different hospitals or went to a particular county or something like that. And for whatever this disease is, not really going to talk about what that disease is, we find that the numbers in here are what we're actually seeing. So, in order to figure out is what we observe different from what we expect, we need to use the chi-squared test. And the chi-squared test, when you look at the formula for it, it is pretty horrendous. And there should be some like i's in here from I equals 1 to n or whatever it is, just because we definitely totally need to math these things up quite a bit. Once we've got the data, as we do, we now get to go and compare what is the value that we observed in what's called a cell versus what we expected for that particular cell. I'm not going to do all of these like by hand, but just to give you an idea of what's going on here. If we're looking at the first cell here versus the first cell here, our chi-squared value would be based on what did we observe? So 1,100 people had whatever disease it is. Oops, that should be a negative there. But we were expecting only 950 people to have that disease. We're then going to square that and divide that by 950. And then for the next one, observed is 20, expected is 50. So we do 20 minus 50, quantity squared, divided by 50. do that for all the rest of the data points in here. And eventually we are going to figure out uh, what the actual chi-squared value is for what we're looking at. That'll help us determine, uh, say, are the numbers that we were thinking about, do they seem to be good enough? Does there seem to be maybe a little bit higher infection rate than, or disease rate or whatever it is we're looking for, uh, versus what we actually saw? So we can use these to come back and try and figure all of this stuff out. We can do that. Yeah, I've got the calculator open. So we've got a couple different ways that we can actually try to do that. You can go around and just come out and use your graphing calc or your scientific calculator if you wanted. Um, you're going to be able to do these calculations without much problem. If we use a graphing calculator, that can be a little bit easier for us. So if you do have a graphing calculator, I'm going to clear this out and clear out this stuff so we can start from scratch if we need to. To do this, we can go to Stat. The first thing that pops up here is going to be Edit, and I can click on the Edit button, and you can see that I've got L1 and L2. And what I'm going to do is we've got four different cells that we're going to be populating in here. One of these columns, we're going to consider that the observed data. The other column is going to be our expected data. And we have to put the data in the same order both times. So if I flip this around, I'm not sure how well you can actually see my screen when I do something like this. But if I'm going to put this in, I can put in, say, this 950, then the 50, then the 4,950, and then the 94,050. So to go A, B, C, D. Down here, I need to put them in the same order. So I'm going to call my L1 the expected values. So 950, 50, and then what else do I have under here? So 4,950. Oops. So let's try this again. 4,950. And then the last one is 94,050. So just so I don't screw this up, I'm going to try to remind myself that all that data that I just put in there is part of L1. And when I say I'm marking this down so I don't screw it up, I'll last term when I tried to grade these, I got the two mixed up and yeah. So I make these mistakes. So try to prevent myself from making mistakes as much as possible. It does that always work out? Sometimes, sometimes not. So anyway, for this next data set, oops, hate having to remind myself that I need to click on everything. So 1,120, and then I have here 3,880, and then for the last one I have 95,000. So once I've got my data like this, I can go back to Stat, come over here to Tests, and then actually come down here to where it says chi-square goof or golf test. The GOF stands for goodness of fit test. So I put all of my observed data in L2. So I put it in backwards, which is the issue that I had when I tried to do the problem from the exam last semester. In order to flip these around, I need to hit second and then 2 because all of my observed data is in L2. And expected value, I need to do L1. And we'll talk about degrees of freedom in a moment here, but for the data that I've got, it is going to be 1 degree of freedom. Now come down here, hit calculate, and you can see that the chi-squared value is 282.57. The p-value is 2.06 e to the negative 63. So what all of this is actually trying to tell us is that there is a very, very, very large difference between what we observed and what we expected. And again, what we expected is based upon, say, some theoretical calculations. We're making some assumptions. And what we've just done here is basically proven to ourselves that perhaps the theory that we're using here isn't actually holding up based, or when we try to compare the theory that we're dealing with versus um, what we're actually seeing in the field. So in terms of, like, say, the scientific method, we collected some data. We went and we tested the data to see if it met, say, some theoretical values that we had. We're seeing that no, in fact, the observed data doesn't even come close. So that's telling us we need to go back. We need to look at our theory. We need to make some changes to our theory and try to come back and say we do these calculations a little bit different way. Uh, with type of thing that we just did here, we I tend to use it a lot if I'm trying to figure out what is the, say, the best distribution to use for a set of data that I have. So it's a concern that for pretty much all of you, you don't really need to worry about all that often, unless, of course, we're looking at the data that was coming from, say, the Flint water crisis. And if you remember back to, what was it, week 5 or week 6, when we actually looked at the data, the scientists and engineers that were trying to deal with that data assumed that the data was normally distributed, but when we looked at it, it starts off high and it comes down low and it decreases the further along we go. That's letting us know that the data is actually exponentially distributed. Or in the case, or so what we did is we tried to undo that exponentialness. And by taking the log normal distribution, all of a sudden it started looking the way that we would expect, which is kind of proof that we what we expected was not, say, what the data was telling us is there. So we need to make some of these changes. With the data that I've got here, it's telling us the same thing. It's letting us know that the thoughts, the theories that we use to try to come up with this data is not actually holding true. So one of the things we can do is we can go back, we can look at the data, we can make some changes to, say, our theories on the data and how the data should actually be handled. Another option is we can actually take the observed data that we have here, and based upon the observed data that we see, we can try to create another set of expected values. And it's this idea that when I was looking at it, or looking at the data from the criminal justice group that's down at Wayne State University, I was watching what they were doing and I'm like, are you sure? Really? Is this actually what you want to be trying to do? And when you look at the way that these things are done, you can actually get yourself into a lot of trouble really, really quickly. Um, the formula for you taking observed data and creating some of these expected values is again a bit horrendous, but let's take a look at it real quick. So the formula, if we don't have any theory at all, and all we're doing is we've just got our data, we have no thoughts on what's actually happening here, and we want to see is what we got different from what we might expect under certain circumstances. What we end up doing is our new formula. So the expected value that goes in any one of these cells here is going to be equal, when we look at the observed data, to the row total times the column total divided by the total. So if we know nothing else about the data, we have no theory to back up any ideas that we might have. This is going to be the idea that, or the calculation that we have to end up doing. And just as an example, if I call this, say, cell number one, cell number two, three, and four, the expected value that I'm going to expect in for cell one. So I've got to look at the row total, 1,120 times the column total, 4,980, divided by the total, which is 100,000. So if we have nothing else to go on, no other thoughts to use here, I can now go back to my calculator, clear all this stuff out, clear all this stuff out. So my row total, 1,120 times the column total, 4,980. And then we divide that by 100,000. And just looking at what we just did here, according to what we just put in here, we should actually be expecting, and these numbers do look really, really weird, but hey, that's what we got. We actually expect there to be 55.78 people in there. Just want to make sure I put the real 100,000 in there. So again, if we have no idea what we should be expecting in anything, we can use that formula. But like we just saw, with our previous expectations, we expected there to be 950 people. With this new expectation where we have no idea what's going on, all that we know is that things are the way that they are in there, we're getting an even smaller number than we had previously. So when it comes to looking at the data using the chi-squared things, Is the research group down at Wayne State trying to do a really good job to help a whole lot of people have better lives? Yes, they are. But because it's something, some like what we just saw here, again, when I'm listening to them talk, when I'm thinking about this stuff, I've got these alarms going off saying, um, "Are- really? Is this really, really what we want to do?" Now, what's going to happen is if we go and we do the rest of these calculations using the same formula, and going to be honest, using the formula the way that we have it in there is pretty horrendous. And no, you're not going to be expected to actually do those calculations on the exam. I know, you're welcome. You're totally welcome. But if we don't have a proper expectation or proper theory or proper thoughts about what we should be looking at, using these tests can get really, really bad really, really quickly. And if you just, without knowing what you're doing, just start using them and mindlessly use them, some of the things that would actually happen if we continued on with all these calculations is we would eventually find that some of the, uh, if we're trying to predict, does this have an association with, say, recidivism or not, we could actually end up getting not only wrong answers, but opposite answers. So when I'm looking at the way that they were doing it and I'm trying to figure out, okay, do you really want to do it that way? These are some of the issues that I have. These are some of the thoughts that I'm dealing with. And needless to say, I didn't get the job with them. But uh, also looking at some of the material that they were doing in this particular project that they were working on, uh, they actually eventually gave up on it. So they gave up or they stopped have or getting the funding for this particular project because they weren't being able to make uh, like say any predictions. They're not able to say to say state regulators or politicians or anyone else who might be associated with criminal justice. Hey, here's how we help reduce recidivism in the people or in a certain population. And to have all that data and then to do something like we're about to do with what we have here, uh, it's horrendous. And I know that I just went over a whole bunch of stuff, and I apologize for that. But I'm trying to remember all the uh, different things that we've actually done before. So, but the thing that we need to deal with here is we need to keep in mind that when we do these chi-square tests, we might only have the observed data, but we should actually use that observed data and try to come up with some sort of a theoretical idea of what's going on. If we don't have that theoretical idea, we can go down a really wrong path very, very quickly. But if you don't have anything to begin with, the calculation that I was just showing you there, that is the essentially the only avenue that we can actually get into. And as you can tell by my state of confusion while I'm looking at these numbers and going, wait, is that actually right? Yeah, it is right. Is the result that we just got there shocking to me? Yes, yes, it is. So if I'm looking at it and I just did the correct calculation, we need to have a better idea about what it is we're dealing with. We need to have a better idea about what we should be expecting from the data. We need to have a better idea about where the data came from. because with a lot of the stuff that we're looking at here, as well as all the stuff that we looked at previously, we've got all these different assumptions that we're dealing with, which is one of them is that the data we've collected is actually representative of the population. Looking at the what we have here, because we were pretending, at least in this case, we went out and collected data from 100,000, say, random people. We can safely assume that the data we have is actually representative of the population. Uh, when we do some of the other calculations that we're going to have for some of the other example problems, again, we need to make sure that the thing that we expect to happen is actually a reasonable thing to happen. So let's get to one of those really quickly. So if we are, and this is actually based on some of the data that they're actually based on an NPR story that uh, list or heard about maybe 5 years ago now. So the data here is a little bit outdated, but again, it's useful in reminding us that when we think about our expectations, we need to make sure that the expectations that we're dealing with are actually true. So let's say we're looking at a tech company and they've hired some software engineers, and let's say they've also hired some administrative assistants. They have, between the software engineers and administrative assistants, they have 1,000 people total that they've hired. They know that they need, say, 900 software engineers, and which also means that they're going to need, say, 100 administrative assistants. And let's look at this in terms of, say, male versus female employees. Now, if we were to look at data from, say, an actual tech company dealing with this sort of stuff, if you go and Google some of this, you should be able to see a lot of these different issues. But when it comes to software engineering, if you look at a lot of different tech companies, you might find that, say, 850 out of 900 of them are going to be male, which means that only about 50 of them are going to be female. When we look at, say, the administrative assistants, uh, we might have, say, 10 male administrative assistants, which would mean that we're going to have, in this case, 90 female administrative assistants. When we calculate our row totals over here, 50 plus 90, 140, 850 plus 10, so 860. And if you're looking at these numbers, and does it look like they have a hiring issue and they seem to be hiring far more men in this company than they do women? And when you look at the data, the way that I've got it here, the answer is a resounding yes. So what are some of the assumptions or what are some of the expectations that we might have when it comes to the hiring process if, let's say, we're going to assume that women are just as good at software engineering as men, and that men are just as good at being administrative assistants as women. So if we assume that there is no, or that women are just as good as men, men are just as good as women in these particular jobs, how many women do we or would we expect to be hired in as, say, a software engineer? If men are just as good as women, and we've got 900 people total, I think we could say 450 men, 450 women. When we're looking at the administrative assistants, again, if we believe men are just as good as women at that particular job, we should see that there are 50 men and 50 women hired in for those positions. And when you look at the data that we had on there, was that even close to the case? And the answer is a resounding no. So the tech company in that was part of this lawsuit was actually sued for gender discrimination against women. And again, looking at the data, if we expect 450 here and 450 people here, and these are the numbers that we actually got, it definitely looks like there is gender discrimination against women. And we expect 50 and 50 people here, 50 people here. You go and you do your uh, chi-squared test. So in this case, these are going to be the observed data. If we think about expected based on what I was just talking about, sorry, I got to draw this stuff out again. So if we're dealing with software engineers and administrative assistants, male and female, again, we would expect 450, 450, then say 50 and 50. So 500 people in this group, 500 people in this group. We get the 900 programmers we want here. We get the 100 administrative assistants that we're looking for. And we have our 1,000 employees. You go and you put everything into the calculator the way that I just did with the other data. You're going to notice that there's a huge difference here. There's a huge difference between these two. There's a huge difference here. There's also a huge difference here. Now, what all of that tells us is that the observed data that we saw is a lot different from the data that we expect. If we're talking about, say, a class action lawsuit against this particular tech company, what you would need to do next is actually go in and try to make sure, or try to see what types of things are actually going on here. It looks like it's a very, very clear-cut case of discrimination based on gender. Uh, and the tech company actually got sued and they lost. And when you look at, well, what were expecting versus what we observed, it's really, really clear why they lost, right? Now, the issue is, where did our expectation for the number of software engineers come from? Where did our expectation for the number of administrative assistants come from? In both of those cases, we assumed, maybe rightfully, maybe not so rightfully, that men and women are equally uh, skilled in doing the administrative assistant job as well as software engineering. And I'm just going to say from a lot of the computer science classes that I took where you learn how to become a software engineer, the women that I've worked with in those programs are just as good, maybe even better than some of the men that were in the programs that I was dealing with. But when we look at who gets hired in, we notice that it's skewed uh, largely to men. So they got sued, they lost, kind of what you would expect in data like that. But the weird thing is that same tech company was sued a second time for gender discrimination. And the second time that they were sued, they were sued because they were discriminating against men. So just looking at the data that we actually saw and thinking about how how could it be that when we look at the data, I'm going to flip it over again real quick. How could it be that when this is what we see, there seems to be some sort of a major discrimination against men? And if you're looking at just looking at the data we have above, and you're thinking, how can there be discrimination against men? Well, again, it comes down to what did we expect? So I'm going to label this as what we expected. The first, or for one of these, what's actually happening, and if you do a quick Google search on this, you should actually see it. If you look, or if you do a quick Google search and you look up, say, percentage of women with software engineering degrees or computer science degrees. And since this is, say, 10 years ago, the numbers are going to be a little bit different now. But there are literally, or there are quite a lot more women getting computer science degrees, but the percentage of women that are getting computer science degrees now, or last time I looked, I want to say it was about 10%. When this case was going through, it was actually more like 5%. So the company needs software engineers no matter what. They need 900 of them. But if only 5% of the graduates of computer science and software engineering programs are female, or even say 10 of them, 10%. So let's go with 10% in this case. We would expect there to be, say, 90 women hired in as software engineers, and 810 of them would actually be hired in as men. Looking at administrative assistants, um, and just using the same type of idea here. And honestly, I have no idea what percent of men would actually want to be administrative assistants. So I don't even have a number that I can put in there. But let's say men and women are equally likely to try to get a job as a administrative assistant. Why? Because I have nothing better to put in. However, if you were to talk with some men that you know and ask them, would you ever think about taking a job as an administrative assistant, they're probably going to say no, just because of a whole lot of really different stupid things from the past. But let's go with 50-50, just to make it a little bit more interesting here. So I'm going to flip this back over. So if we assume that there should be 50 here, and if we assume that there should be 50 here, again, we have our 100 people here. Over here, we have our same 140 from before. Over here, we have our same 860 from before. So now, sorry, software engineer, administrative assistant. So this is what we expect based on, say, data from graduate schools and all that sort of stuff. And these numbers are probably going to come out a little bit different. But what we're going to notice, yeah, and again, when I'm trying to do these numbers on the fly, things can not work out quite as well. Probably should have used the 5% here, but let's use what I've got here and let's just see what's actually going on. So hopefully you can still see my calculator, clear that stuff, clear this stuff. Going to put the data back into the calculator. So observed is going to become L1. So I'm going to say this should be 850 and then 50 down here. And then I'm going to make that 10, going to make that 90. Did I just do that in a different order from before? Yes, I did. But the important thing here is that we have to follow in the same pattern. So 810 versus 90. And then over here, 50, say versus 50. Oops, should be 50, not 59. Let's try that again. And now observed is L1, expected is L2. So now when I go back to stat, come over to the chi-squared test, come down here to that goodness of fit test again, and I hit the enter button here. Observed is now L1, so I have to change that by doing second and 1. Expected is now L2, so I need to change that to second and 2. Degrees of freedom are the same as before. Going to come up here and hit enter. And what we're finding is that, again, there seems to be a significantly different result compared to what we observed versus what we expected. The p-value here is 5.6 e to the negative 20. So this p-value that we're looking at right here is 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 where the observed data doesn't really conform to what we are expecting to have happen here. And we can actually look at where it says the contrib right here. We notice that there doesn't seem to be a very large contribution for the difference between male software engineers that were hired versus the number of male software engineers that we expected. But the second one here, so we observed there to be 50 and we expected there to be 90. So there is a very large difference there. And the difference in, and again, because I'm trying to use numbers on the fly, it's not working out quite the way that I was thinking it would. But in this particular case, it does look like there seems to be a very, the number of female software engineers based on 10% are hired in versus 5%. It looks like we don't have as many female software engineers as we would expect. And if we could actually get the contribution stuff to go all the way out, we could look at it and see that the difference between the administrative assistants for men versus women, the contribution there is going to be fairly huge because we expected there to be 50, but there was only 10. And again, if I'd used the 5%, we probably should go back and use the 5% on this. What we're finding, based on that data is that there, or, well, sorry, trying to get ahead of myself again, sorry. If I use the 5% data, like we probably should have, what we would have found is that there is a significant, or that there are significantly fewer men that were hired in than perhaps there should have been. And when you look at the data for what was observed, if you don't know that there aren't that many women that are in software engineering or even eligible for those jobs, um, what's going to happen? Essentially, what we're seeing, or with this data, is what we would actually expect. And normally, when I'm talking about this stuff, uh, be, the shortage that we have between male or men and women in software engineering and even in a lot of the different STEM fields is actually still fairly large like that. Soft computer science, engineering tends to be very, very male skewed, the way that we're seeing the data here. And one of the things that some of the software companies, like say Facebook, Google, places like that, actually tried to do is they pledged to hire more women to make the number of women that are programming and doing the software engineering stuff at their facilities more equal to men. Unfortunately, if you look at the number of women that are graduating, just the sheer number of women that are graduating with software engineering degrees. One of the things that you notice if these tech companies actually wanted to have 50% men, 50% women as a software engineer, some of the women, essentially all of the women that are graduating for the next, say, 5 or 6 years, would literally all of them would have to agree that they are willing to work for a company like, say, Google. And then maybe Google can get the number of women that they're looking for. Let's try to make this a little bit bigger soon. All right, that's not doing anything. Sorry about that. So anyway, um, with something like this, is there going to be a significant number of men that are working as software engineers now? Yeah. Is it going to continue on into the future? That's also going to be happening. Why? Because a lot of women look at software engineering, they look at computer science, they look at the traditional engineering programs and think, no, that's not for me. I want to do something else, which is totally fine. But in these STEM fields like engineering and computer science, what ends up happening is it's male dominated. And for the foreseeable future, because of that, a lot of the jobs in those areas are actually going to go towards or go to men. And if and I think software engineering right now is probably a really bad job to be talking about because artificial intelligence is actually taking over quite a bit of the jobs that software engineers have been doing in the past, anyways. But the idea here is when we look at it in the first case, we noticed that if we assume that women are just as good as men, we're going to come to some conclusions about it. But when we dig just a little bit deeper and we recognize that, say, 5% or 10% of all women, or sorry, of all software engineers are female, now all of a sudden the numbers that this tech company had originally, they still look bad, but they don't look as bad as they were before, which is why they got sued for a second time. And in that second time, they got sued for being biased against men, even though 86% of the employees they had were men. Because there's so few women in software engineering, it probably should have been more like, say, 90% men, which is weird, which I totally admit. But it is a thing that comes up. And it is getting back to the idea that I was trying to get in or tell all of you about, which is when we do these chi-squared tests, we need to make sure that the expected values that we're dealing with are actually, say, valid. Again, if we have no idea what any of these numbers should be, we can use the numbers that I'm showing you, where we have the expected value is equal to the row total times the column total divided by the total. And again, no, you're not going to be doing those calculations. You're welcome. Uh, in a previous or at a previous university, one of the professors there actually had all the students on the final exam do calculations like that. Uh, we're looking at what would be called a 2 by 2 chi-squared test. They had students looking at a 6 by 6, meaning that formula that I was showing you, the students would need to use that formula 6 times 6 times, so 36 times to do the calculations. They also needed to calculate all of the column totals and the row totals in order to figure out what actually goes into that formula. And I actually looked at the professor who wrote the exam for everyone and told them, I know exactly how to do it. I know every shortcut I can take in order to do those calculations. And if I'm doing this problem on the exam, it's going to take me 10 to 15 minutes. How long is it going to take my students? And the professor just kind of looked at me and went, well, that's your students' problems, not mine. Does that seem a bit mean? I think so. But anyway, I'll I'm going to do one more of these calculations really quickly. This is actually something that is similar to what's going to be on the exam. So when we're looking at, or when you're thinking about prep for the exam, what types of questions are going to be on there, this is actually going to be one of them. So what's happening here is we're going back to our uh, Flint water crisis data. So I've got, well, 1, 2, 3, 4, 5. You have 6 different cells. 34% of the data from theory should go in here. 34% of the data should actually go in here. 2.5% should go in this outside one. 2.5% should also go in this outside one. And I believe it's what, 13 and a half, 14 and a half. Let me check it real quick. So what's happening is we are looking at the normal distribution. And if we go from X bar plus 1 standard deviation, that should be 34% of the data, which is what we have here. If we go from 1 standard deviation to 2 standard deviations, which is this value over here, which is basically going to be 50 minus 34 minus 2.5. Yeah. So that's going to be 13.5% of the data out here. And if we go 2 standard deviations, say out to infinity, that should be 2.5% of the data. Coming back the other way, X bar minus sigma, 34%, 1 sigma to 2 sigma. Again, that should be 13.5%. And then the last little bit, again, should be 2.5%. So if we're looking to test data, and let's say we're looking to test the Flint water data and see if it's normally distributed. We already know that the data was not normally distributed. But if we look at it in terms of average plus a standard deviation, or uh, average minus a standard deviation, and then average plus two standard deviations, average plus three standard deviations or more, x bar minus two standard deviations, and x bar minus three standard deviations, the way that we've got it now, we would expect 2.5% of the data to be here, 13.5 to be here, 34% to be here, 34% here, 13.5% here, and 2.5% out here. So if we are now going to be looking at, say, let's say when they started gathering the data instead of the 78 samples that they had or whatever it was, let's say we're looking at 100 samples. Of those 100 samples, how many of them, so this is going to be the expected number. Out of 100 samples, we expect 2.5 of them to be in the, or 2.5% to be out here. You multiply those together, you get 2.5. 100 times this 13.5 is going to be 13.5. 100 times 34% is 34%. 100 times 34% again is 34%. 100 times 13.5 is 13.5. 100 times this last little bit out here is again going to be 2.5. So if we pretend, or if we want to assume that the data is normally distributed and we only have 100 of them, this is how it should be according to theory. Now, when you look at the data for real, so it's 3, 4, so 5 and 6. So again, this is the x bar minus 3 sigma. The real data had 0. Out here, this is x bar minus 2 sigma. Again, this data out here had 0. X bar minus 1 sigma. I believe this was like, say, 50 here. When we look at x bar plus 1, so we're getting to larger values. I don't remember exactly what the values are, but let's say it's 20, and then say 15 and 15 or something like that. We now have our observed data. We can plug it into the calculator. We know what our expected data is based upon theory, and just looking at what we have versus what we expect. When we plug it into the calculator, we are going to find that there is a very significant difference between what we saw and what we expected based upon we expect there to be a normal distribution of the data. So when we analyze the data like this, it's going to come out to be statistically significant. It's telling us that there's a statistically significant difference between what we expected, assuming a normal distribution, versus the data as it actually came out. If these scientists and engineers that were looking at the Flint water data had done these types of calculations, this would have been telling them your assumption about the normal distribution is not holding up. You need to go back, you need to look at the data, you need to change your expectation for what should be going on here. And there's a chance that if they had done this type of thing properly initially, um, the Flint water crisis, it still would have happened. But like I was telling or talking about before, it wouldn't have been as bad as it was. And unfortunately, people still would have been subjected to high lead levels in their drinking water, but it would have been 2 months. It would have been, say, 3 months instead of the year to year and a half that it actually was. So again, if you use the chi-square test properly, if you have the proper expectation of what you should be seeing and what you should be getting, you can realize very quickly that the data you have does not meet what your particular expectation is. That gives you the opportunity to come back and try to tell or see what's actually going on. If we changed our expectation for the data to go from being, say, normally distributed to exponentially distributed, the way that it looked to us, when we look at these 5 or 6 cells, we would actually be getting a much smaller chi-squared value than we had. Um, when we're looking at the data, we're trying to figure out what is the best distribution. A lot of times, though, and I might get in trouble for saying this if you talk with some status or some theoretical statisticians about it, but all the stuff that we talked about that went on to the first exam, where I said, okay, this is the binomial distribution, this is the Poisson distribution, this is the normal, this is the exponential, and everything else. Those are basically our best guesses. Real data doesn't 100% conform to any of them, but the best that we can, or for us, the best that we can do is hope that the data looks close enough to one of those so that we can then go back and use those calculations that I was showing you and we did in the first half of class to make predictions about what's the probability this is going to happen, what's the probability that's going to happen. And you can say, well, if real data doesn't conform to anything, why did we bother torturing all of you with using the traditional statistical stuff? Well, the answer is if you want to try to do this with the data without using any of these distributions, um, I even have trouble doing some of those calculations. And if I have trouble doing the calculations and I have a degree in this stuff, do any of you think you're going to have a chance? And I'm not saying that to be sarcastic or put anyone down. I'm just saying, seriously, uh, can anyone here do triple integrals over certain areas to do all sorts of different math things? No, probably not. Maybe. It'd be cool if you did, but with doing it the hopefully proper way, yeah. Uh, using the data and without thinking about any of these distributions. The class that we're taking right now literally goes from being difficult, the way that a lot of you are experiencing it, to almost simply impossible. So, which is why we cover that stuff in the beginning. We know that real world data doesn't completely conform to it, but the best that we want is we hope that it's close enough, similar enough to some of these other distributions. And I'll we'll actually do the calculation on this in a moment, and I will use Excel to show all of you how you can do it using Excel in case you do not have a TI 84. And I will leave chi-squared as it is. I'll have to talk about degrees of freedom too, but we'll do that in about 10 minutes. Can anyone else tell that I'm kind of really tired right now? Or is that just me? So let's give it 10 minutes. We'll talk about degrees of freedom and how you calculate them. Fortunately, those are really easy formulas to deal with. The chi-squared stuff, doing these expected values and everything else, that can be a real drain. Okay. So let's give it 10 minutes and we'll get started back at 7:05. And uh, because I've been talking for about 9 hours today, I'm going to go grab something to drink. So I'll be back in a moment.
Next week I do have a Zoom in like I'll only I should like I'll be able to my Zoom's at 6 for another class, but it's to go over the final. Um
Hmm.
and it's also worth some extra credit, and I need extra credit in that class.
Yeah,
So
no problem there.
I'm not sure. She said it's only going to take like 45 minutes. So I might be gone for next week. But if I have any questions over the homework, I'm gonna try to get it all done, like I said, either tomorrow
Yeah.
or Friday. And if I have any questions, I will email you. But would you be available possible for a Zoom on Monday if I have any questions?
Um, on Monday, I teach 8:30 in the morning until 2:30 in the afternoon. So if you wanted to meet at uh after 2:30, play it safe, probably call it 3. That shouldn't be an issue. But if you're like, I need help at between 10 and 11 a.m., just gonna be honest. No.
Yeah, it would probably
Uh,
be in the afternoon because I don't usually get out of work until like at least 4, sometimes 5. So it would be um around that time. But if I'll see how my homework goes, and then if I don't have any questions, then I won't. But if I do, I will shoot you an email if that
yeah,
works.
no problem there.
Perfect. Thank you.
Mm. All right, so unfortunately, it's time to get back to some of this learning stuff. So if you look on the screen, you should be able to see the Excel spreadsheet that I just kind of opened up. Haven't done anything with it yet, but we know that we can go in and calculate chi-squared values. The chi-squared values, again, are going to be the observed value minus the expected value, and that whole quantity is going to be squared. And then we're going to divide that by whatever our expected value is. So I can actually go quite a bit larger on this. So just as an example, a blank formula for this. So if I'm trying to prepare Excel for doing these calculations, I can actually type in equals, open parentheses, since I'm going to take the observed value, subtract the expected value, close the parentheses, and then raise that, so the observed minus expected, and then square that. I can use the what I've got on the screen right now, and then I should be able to hit divided by the expected value and hit enter. And right now it's going to give me this weird hashtag div 0. It's trying to tell me that I'm trying to divide values by 0 here. So let's actually put in some of the values. So if I put in 0 and 2.5 here, if it works out, should get 2.5, because what's essentially happening is we have 0 minus 2.5, which is negative 2.5. We square that, and then we're dividing it by 2.5. So it comes out to be 2.5 squared divided by 2.5, which is the 2.5 that we have here. Probably not the best values to be trying to explain this calculation with. But if we now flip this over as well. So again, our expected values are everything that we've got here. The observed values are everything that we have here. So for the second cell, I'm going to do 0. Oops. And then the corresponding value that should be there is 13.5. Since I only did this for one of these, I can take this, drag it down, and it's going to do these calculations for me. My next one is going to be 50 versus 34, then 20 versus 34, and then 15 versus 13.5, and then 15 versus 2.5. Oops, that should be 2.5, not 2 comma 5. So down here, I can type total equals, and then the chi-squared value that we want is actually going to be equal to the sum of everything that we just calculated. And you can see, based on this, the chi-squared value is going to be 91.9608. This will tell you whether or not there seems to be, or when we compare this value against a chi-squared critical value, this will tell us whether or not there seems to be a statistically significant difference. If you do this um, with your graphing calculator, it's going to give you the p-value and all that. But what's happening here is we've got our chi-squared value, which looks a lot like the f-test that we were doing a while back. And it's exactly the same types of thoughts and principles. If for a certain number of degrees of freedom, let's say the chi-squared value, or chi-squared critical value is equal to 6.0, we just did this calculation and came up with a 90, was it 91.96? So if this is 6.0, 91.96 is going to be way out here. So I just have to keep drawing this out for a very long time. So what's happening is the 91.96 that we have out here is very much larger than our critical value that we have back here. This is telling us that we are basically going to reject H naught. This is telling us observed is not what we expected. So now we can go back and try to figure out why why that happened or why that is happening. And if we do a little bit more computer programming on with Excel, we can actually calculate the p-value and everything else. But the thing that we need to really worry about here, though, is what are the degrees of freedom that we need to put in? There are actually going to be two different formulas here. You are going to be expected to know what both of these formulas are. Thankfully, these calculations are not extremely difficult to do. So number of rows minus 1, number of columns minus 1, or number of column 1, number of cells minus 1. So if we're looking, oops, if we're looking at data like we were just looking at here, how each one of these boxes is counted as a cell. So how many cells do I have? 1, 2, 3, 4, 5, 6. So for this, degrees of freedom is going to be equal to 6 minus 1. So it's going to be 5. If we're looking at something like this, what we have to remember, or what we have to calculate, is based on what are the values that we were looking for in the first place. Not the values we calculated elsewhere, just the number of what are the values we were looking for in the first place. So the number of rows here is 2. The number of columns is 2. So in this case, degrees of freedom is going to be equal to 1. For the problem that I was telling all of you about, where one of the professors did a 6 by 6. So let's see, 1, 2, 3, 4, 5, and 6, and then 1, 2, 3, 4, then 5 and 6. Degrees of freedom here, again, the number of rows. So it's going to be 6 minus 1 times the number of, so number of rows, we got 6. Number of columns is also going to be 6. So 6 minus 1 times 6 minus 1, or 5 times 5. to give us, oops, sorry about that, to give us 25. Now, again, imagine you're given data in something like this, and now you're told to use um, the calculations that I was showing you before, where the expected values are equal to row total times column total divided by total. So you're going to have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 calculations to get all the row totals and column totals. You then have to do 6 times 6 or 36 of these different calculations to fill in every single one of those cells in order to figure out whether or not you might possibly have a statistically significant difference between uh, what you saw versus what you expect based upon you have no previous knowledge or idea about what could potentially actually be happening. So when I was talking with the professor that wrote that question, and I told her it's going to be take me like 20 minutes to do, and I know what I'm doing. What ended up happening was a lot of my students in that class actually had some really, really horrible things happen. And like they didn't get it done. I gave them as much credit as I could, but thankfully the question was only worth like 5 points on the final exam out of 100. So you put in an hour and a half of work for 5 points, doesn't even really seem worth it. Um, but so we can see what the formula here is one more time in case anyone needs it. I can actually create a Excel sheet, or actually have created an Excel sheet where you can actually put in all the data points the way that I've got it set up here. However, it is going to be, or would be on all of you to know how many degrees of freedom you're dealing with so that you could actually fill in the Excel sheet. And I can make that available for the second exam as well as the final. But if you want to try and make it on your own, you can see the formula that I used to at least do some of these calculations. So with a lot of these chi-squared calculations, uh, like I said, I use them if I'm trying to figure out what is the appropriate distribution to be using for different types of data sets. And thankfully, the software that I use will actually do all of that for me. If I know I can use SPSS to do these types of calculations as well. And that is actually the software that the criminal justice people in Wayne State were using for their particular project. Uh, I'm not really that big into using the chi-squared as it is, as you can probably tell. We will actually talk about a much better method for doing chi-squared as opposed to having to do all this stuff. But chi-squared does have its uses, and basically the two types of calculations that we did, those are essentially going to be the types of calculations that are going to be on the exams. So hopefully it won't be too difficult. There are a lot of the videos that I've done for the previous online classes that you all have access to, where I do quite a bit more of these calculations, and also do it when I'm a whole lot more awake than I am right now. So I do apologize for that. So, uh, with the chi-squared stuff, we've got we have a basic idea of what we're supposed to be doing with it and how we can actually use it. And again, the main idea when we're trying to use chi-squared is make sure that when we're trying to come up or figure out what is our expected value, try to make sure that we actually know or have some sort of, say, even a theoretical reasoning for why the numbers are the way that they are. If we have that, it's very easy. If we don't have that, it can get to be very awkward very, very quickly. Uh, just looking at the syllabus, I had it on here somewhere. I think this is it. No, sorry. Right class, wrong university. And of course, I can't get on here to exit out of that. Here it is. So looking at the syllabus, like I said, we are a little bit behind. Not worried about it because with all the stuff that we're doing, uh, I always pack in extra material. And then when things, something like we get slowed down a little bit, don't really have to worry too much about that. But you can see, like this week is the week of November 3rd. We supposed to be doing linear regression and that sort of thing right now. And then next week, I'll do a little bit more on linear regression. Logistic regression and linear regression are very, very similar to each other. But then look what happens in about 2 weeks. So you're going to be having exam number two, and then time off for Thanksgiving, review for the final, and then at some point, you're actually going to be doing the final fairly quickly or fairly soon. For material that's going to be on the final exam and exam number two, it is going to be this linear regression stuff. So we actually have some time to go over linear regression tonight. We'll do a little bit more linear regression later on or next week. And hopefully can get back up to where we get to all the grades on here. So there's supposed to be 100 points of a journal review. You should have already done one of those journal reviews for the first half. There will be another journal review for the second half. That journal review will be due essentially the week before the final exam. So the week when you would all be studying for the final would be when this is due. So you're going to have about a month to do it. And I will write this down so that everyone can see it. But this second journal review is going to be on, again, uh, some medical condition that you are actually interested in. But this time, we're going to be looking at how can you get, say, more reproducible results for, say, testing whatever disease it is that you happen to be dealing with or interested in. So we saw in week two of class, a lot of times if you have a standard screening test, there's going to be a false positive rate, there's going to be a false negative rate. That can be, or there can be a lot of issues with reproducibility because of something like that. But with this journal review, just to give you some ideas of where you should actually be looking for this, would be in, say, the implementation of artificial intelligence for analyzing, say, medical charts and see how essentially you can see how well does artificial intelligence do at, say, predicting someone has a particular disease versus, say, what's been happening with the doctors who are uh, trying to predict that exact same type of disease. And a couple hints to give you an idea of where this is probably going to go. Might not go with the particular disease that you're looking for, because I don't know what everyone's going to be interested in looking at. But there is a chance that if you look up or if you do a little bit of a Google search on IBM's Watson system, with IBM Watson, they looked at a lot of medical charts, and IBM was actually trying to sell Watson to a lot of different hospitals as a way of, say, helping diagnose various diseases. And if you Google IBM Watson for medical or for hospitals and stuff like that, you'll kind of see what happened. Don't think they're around anymore, which is telling me that that whole system, IBM spent millions of dollars on it, didn't quite work out the way that they wanted. Part of the reason for that is because of unreproducible results. So, going to be looking at reliability and reproducibility of results. And I will say, even if the only thing that you're looking at is, say, cholesterol testing, there have actually been quite a few really well written articles on cholesterol testing. So, and are those results actually reproducible and how reliable are they? And like a lot of the different lab tests that we can actually look at, the answer is sadly not very. So let's take the rest of the class today and then all of class next week, and we will be talking about linear regression and how we can actually use it in our data analysis. And hopefully, I will have a uh, a lab as well as a homework for the linear regression stuff that you can actually work on so that you have a better idea of what's actually going to be coming up on exams. Right. Well, exam number two as well as the final exam. So let's flip this over again. And I actually don't need uh, pretty much anything on my computer the rest of the night, so I'm going to stop sharing. All right. So when we're doing linear regression, uh, looking at it, when we looked at ANOVA a couple weeks ago, anything we do with ANOVA, we can also do with a linear regression. And if you remember, anything that we do with a t-test, we can do with ANOVA. And if we can do it with ANOVA, it means we can also do it with a linear regression. A lot of you are already familiar with one of the most basic models that we can do with linear regression, which is basically just going to be y equals mx plus b. So hopefully you all remember y equals mx plus b from Algebra 1, Algebra 2, however many years ago you actually took it. Just as a reminder, the m is the slope. The b here is the intercept. And with the slope, if you remember back to your days in algebra, there's actually a formula that you're supposed to use to figure this one out. No, you're not going to be using it here. Uh, Part of the reason is when you did that calculation back in algebra, you had two data points. When we're doing it with the real data, we're going to have hundreds, potentially thousands of data points. So the formula that you had and any anxiety you may have based on y equals mx plus b, uh, don't worry about it. We're going to have all sorts of new anxiety inducing things popping up with this. So what we do with the linear regression, and once we get into some of the stuff next week, is uh, going back to, say, t-test, going back to ANOVA. One of the assumptions that we had with both of these was that there was only one change between groups. So what do I mean by that? So just as an example, if we're looking at, say, medication A versus medication B, we believe that, or for t-tests for ANOVA to work the way that we want them to, we have to assume that the group of individuals that are in, say, the medication A group are essentially the same as the people that are in the medication B group. And that the only major difference, the only difference that, say, really matters is that group A got medication A, group B got medication B. And we talked a little bit about how uh, assumptions like that may or may not actually be true. We also talked about how when I was doing some educational research many years ago, we some of the people that I was dealing with would be asking me to do things like, say, compare 18 to 21-year-old Black females versus 31 to 40-year-old Hispanic men. If you think about those two groups, is there only one thing that's different between the two of them? Well, if you were to come out and say, well, race or ethnicity is the difference between that, well, there's also the age difference. So when we have all of these different things that are being changed simultaneously, uh, they can be, or they're called some, or there's something called co-founders or confounders. Um, if we if everything that we have between these two groups is essentially the same, other than that one thing that we're testing, uh, having all these different confounders doesn't really make any difference for what's going on. Uh, if they are truly not the same, we just have to, and we're just pretending that they are the same. Uh, a lot of the analyses that we could do are actually going to fail. And it's going to fail because there's more than one major change between the groups that we're dealing with. With linear regression, and when we look at it next week, and we're talking about multiple linear regression, one of the things we can do there is actually look at the effect of, say, 15 different things, 20 different things on the outcome that we're interested in. We might So if we're going back to, say, group A versus group B with this medication, uh, if we're just doing it as a t-test, again, we have to assume that there's only one major difference between group A and group B. That one difference is going to be what medication do they get? With linear regression, we can look at uh, the one or the difference between those medications, but we can also take into account how much does every person in group A as well as group B weigh? What is their blood pressure? What is their white blood cell count? What is their red blood cell count? What is their cholesterol level. If we're talking about, say, pain medication, uh, and we're looking at how effective the pain medication is, what was their pain rating beforehand? What is their pain rating after they take it? And we can uh, take all of these other things into account. We can even look at, say, do the people in these groups have uh, for myself, I actually have a couple of compressed discs in my lower back from working out improperly many years ago. So I have chronic back pain. Uh, how is that going to affect, uh, say, how effective a new pain medication is going to be? If we're talking about, say, physical therapy, if I've had compressed disc in my lower back and chronic back pain for the last 15 years versus someone else who's had it for, say, 3 years or 2 years, could those differences actually make a difference as far as how much, say, pain relief or something I get when I start going to one of your classmates' physical therapy studios? Um, if you don't know, well, this is a way that we can actually find out. The big thing that happens with linear regression is we are actually looking for something called correlation. The more correlated things are, the stronger the correlation is, the more likely it is that we're going to find that whatever that thing is that we're interested in, will be statistically significantly different. In the case of what we're doing here, we're looking at the difference between there is zero effect versus there is some effect. The effect that we're looking at could be positive, could be negative. The way that we're going to figure that out is by looking at the slope that we're dealing with and comparing the slope against some of the different metrics. I'm not going to start pulling up a lot of the stuff right now. We're just going to go over some of the different ideas here. Uh, but we essentially comes down to we look at a confidence interval. We look at the confidence interval for the slope. If both of the values in the confidence interval are negative, that's telling us that whatever this variable is has a negative impact on the outcome. So, uh, like a way that we can think about it is suppose for a moment that we are dealing with, say, some sort of a medication, and one of the variables we're looking at is, say, is the patient already on a different medication? And let's say those two medications are actually interacting with each other, and patient that's on this other medication, that medication makes the new medication we're testing, say, less effective. If it's going to be less effective, the slope that we're looking at is actually going to be negative, meaning at the more of this other medication the patient takes, the less effective the medication we're studying is going to be. By taking all of our data like that, it makes it a lot easier to actually see what's going on and a lot easier to give a very, very nuanced answer when, say, a patient asks, how effective is this going to be for me? The doctor or the physical therapist would be able to look at the uh, regression model that we have or that was created and would be able to say, okay, sir, okay, ma'am, okay, uh, whomever, because of your body weight, because of, say, your BMI, or if we know, say, percent body fat, something like that, because of your blood pressure, because of this, because of this, because of that, we think that the effectiveness of this particular medication might be really small. Whereas you look at someone else who has a lot or who's very different from that initial person, you might find that the effect of the medication is going to be a whole lot larger. So if you are a doctor, if you are a physical therapist, being able to use multiple linear regression or multiple logistic regression, which we'll talk about a little bit next week, you can actually start taking into account a lot of the different factors that are going on, as opposed to with the typical or with the t-test, where we just assume that there's only one difference between the two groups, and we're just looking at, say, the one medication, where if someone comes to a doctor and says, how effective is this medication going to be for me? They're going to say, oh, the medication's that effective. Well, it's that effective on average. Like I was saying, if you take certain other medications, it might be they're a lot less effective. Under certain conditions, it might be a whole lot more effective. If all we had is the t-test, all I can say is, no matter who's talking to me, the answer is it's this effective. Uh, so having that as a or having the ability to look at that sort of stuff is actually going to be a really, really useful thing. Because we are talking about public health, I used to work as a chemist for an environmental contamination testing facility, actually three or four different ones. Uh, and some of the stuff that where we would use a regression model like I'm talking about here is if we wanted to try to do something called create a calibration curve. With a calibration curve, basically, and if you any of you are working in a hospital and you're going to be working with instruments that are going to be measuring, say, white blood cell count, red blood cell count, say, blood alcohol level, if you work in an ER somewhere, if you're looking at what is the concentration of, say, illicit drugs that are in a person's blood sample, and things like that. These calibration curves are going to be appearing in the work that you do daily. Uh, with the calibration curves, or at least the ones that I've worked with. So for those of you that are doing, say, white blood cell count, red blood cell count, and you're using instrumentation to do that, the calibration curves you're working with are going to be a little bit different from the ones I did. But the thing that I'm trying to do is I'm trying to predict what is the concentration of a particular chemical of interest. A lot of times, the chemicals that I was actually looking for are highly toxic. So, yeah, I got to play with the toxic chemicals all day long. And one of the ways we could tell what was the concentration of all these really toxic materials was to put them into the instrument. And the instrument's going to do what the instrument does. If you want to figure out what's going on with the different types of instruments that you might use on campus here, there's a chemist or pair of chemistry classes called analytical chemistry and instrumental analysis. They're both offered through the chemistry department. If you go in there, take those two classes, uh, you can start getting an idea about calibration curves, what they're good at analyzing for, how they analyze for it, and all that sort of stuff. For this class, we just need to know that uh, when the instrument does what works its magic, it's going to come out with something called a chromatogram. And when you look at the chromatogram, it's basically going to be a flat line until the one of the sensors on the instrument starts to detect something. As it detects, the line is actually going to increase, and then it's going to make a peak and then go back down to what its baseline is. Or at least that's what it should be doing, assuming that it's actually working right. And what we do is that peak that we have, We find out what is the area of that peak. We put that area of our peak into our regression line, which is essentially y equals mx plus b. And then we try to predict y, which is going to be the concentration. To do these calibration curves, we actually have to do the opposite way first. We know what the concentration is, then we look and see how big of a peak we get. And we do that with, say, 10 or 5 to 10 different concentrations. I used to do mine looking at 9 samples or 9 different concentrations. Some of the people I worked with would do 4. What is the correct number to do? The correct number to do is however many you need to do in order to do the job that you're doing. Makes complete sense, right? Or what's the other way of putting it? It depends. Hmm. So, uh, but just as an example, uh, you could think of it kind of like a currency exchange. You know that $1 is equal to, say, 50,000 Turkish lira. You know that $2 is going to be worth 2 times that. So 100,000 Turkish lira. You know that $10 is going to be worth 10 times that, and so on. So if someone comes back to you later and has, say, 70,000 Turkish lira and wants to convert it to US dollars, you know, based on dollars to lira, how to go from lira back to dollars. And that's what these calibration curves do. They allow us to figure out about how much of the sample is in there. Some of the things that come up with the calibration curves, if you've ever worked with them before, you know uh, how some of the values come out. You compare, sorry, some of the values for the slope come out. If you know, if you've had other stats classes or if you've working with, say, a researcher on campus after this class, when you do your regression models, uh, you'll know that the slopes that you're looking at can be all sorts of different sizes. And they're actually, now I've actually seen some people who can think that they can look at the slope and actually determine whether or not it's statistically significant based upon the size of it. So this will be a little bit of math, but not too bad. So let's take a look at what I'm talking about here. Let's say we're looking at what is the concentration that we're looking at, and we know that it's equal to some slope times some area. If the instrument or if an instrument that I'm using in one of the labs is actually working right, this plus B thing, this is going to be approximately 0. So I don't even need to work or worry about it at all, which makes this a little bit easier. Now let's say I put in a sample and the concentration that I know is in there is 0.50, let's say ppb. When we look, if we're trying to figure out what this M value is, when we look at the area on some of the instruments that I've seen, it has something like 10 to the 9. What does that mean? So 1 billion. So now we have 0.5 equals M, some slope that we don't know what it is, times 1 billion. How do we get M by itself? And no, you're not going to be expected to know how to do this on the exam. So don't worry about it too much. Just sit back and watch it and then see what's actually going on here. I can divide both sides by that 1 billion, and I'll have zero point 0.5 divided by a billion, which means that this m is going to be really, really small, on the order of, say, if this is 10 to the 9, the value here might be 10 to the negative 8. So what does 10 to the negative 8, or as your calculator might produce a 10e negative, or sorry, just e negative 8. So what does that mean? Be like 0 0.1, 2, 3, 4, 5, 6, 7, uh, 8. So whatever that value is out there is going to be, whatever x is actually going to be some sort of a number. So these slopes can be really, really small, but just because they're really, really small, that doesn't mean it's not statistically significant. And I've actually seen some people when they look at how some of these things come out and some of these coefficients are set up, they will actually say, well, clearly there's nothing going on there. But then you have to remind them, really small number times really big number gives us zero point 0.5. So even though the slopes here are going to be really, really small, we can't let that fool us into thinking that small means that it's not important. Because if we did that, then literally all the analytical work that I did would not actually be possible. Um, some of the stuff that I was actually able to do using these types of linear regression models as well, and this is actually similar to a question that's going to be on the exams, is I would run a type of a chemical analyte, so a thing that, and this is going to be a concentration of a chemical that I know for certain is actually in the sample because I put it in there. And I put it in there at a certain concentration. And one of the things that would happen is when I go to run my instrument, uh, you could think of it like, say, using a change machine, and a really bad change machine. If the instrument is working properly, you can think of it like you go to a really bad change machine, you put $1 in, it's never going to give you exactly $1 back. But if you put in, um, but if you put in that dollar, you're going to get something close to $1 back. So say somewhere between 95 cents and $1.05. On average, it's going to come out to be you put $1 and you get $1 back, but it's never actually going to be exactly $1 of you put in and $1 and change coming back. Well, with the instrument that I was running, it was even worse than that, but it was also predictable and predictably bad. It would start off giving you about 70% of what it should have, and then it would creep up, creep up, creep up to 130% of what it should have been. In cases like that, what would end up happening is if I put a sample in there at the beginning of the day, and then I put that same sample in there at the end of the day, at the beginning of the day, it'd be, say, 75% of what it should be. At the end of the day, it'd be, say, 125% of what it should be. So basically, the amount of analyte that's in these samples would go up and be, say, 50, technically 50% more, or there's a 50% change there. But depending on what it was, a lot of other weird things could be going on with that. But it'd be like, imagine if, say, you go and you weigh yourself, say in the morning. I don't know how much anyone here weighs, but let's say you actually do weigh 200 pounds. You weigh yourself in the morning using a scale that worked the same way that this instrument did. In the morning, it told you that you weighed approximately 75% of your true weight. So if you weighed 200 pounds, 75% of that would come out to be 150 pounds. If you weigh yourself on that same scale at the end of the day, when it's telling you that you weigh 125% of your true weight, it's going to tell you that you weigh about 250 pounds. You actually weigh 200, but in the morning it's 150, at the night it's 250. So because of issues like that, I had to keep track of how bad the instrument was. And from time to time, we would actually go and do a calculation on how to correct our samples or the concentrations we were looking at based upon things that were actually going on. So to give you an idea of what that calculation looked like, over real quick, what would end up happening is we would have a reported concentration. The function that we would have here would be, say, 70% of what it should be, plus, let's say, 3% times what's called a run position. So if this is the first sample of the day, the run position here would be 1. If this is the 30th sample of the day, the run position here would be 30. So just so that we have something here, let's say run position 2 versus run position 10 versus, say, run position 15. So the reported percentage, I should say here, is going to look like this. This is same thing as the linear regression model that we have here. So what's going on is if I ran a sample in position 2, the reported percentage is going to be 70% plus 3% times the 2. 3% times 2 is 6. 70% plus 6% is going to give me that 76%. If I'm at run position 10, I'm going to have 70% plus 3% times the 10. So 3% times 10 is 30. 70 plus 30 is going to be 100%. If we look at this last one, 3% times 15. So 3 times 15 is 45. 45 plus 70 is going to give us what? So at 10, it was 100%. 70 plus 45 is actually going to give us 115% of what we had. And if you're looking at this and you're really annoyed by it, I totally understand. But what was that? What actually was happening is if I ran the same sample 3 times in the day, earlier in the day, it's going to tell me 76% of the total amount of analytes I'm looking at. If I ran it in the middle of the day, it'd give me about 100% of the analytes. If I ran it a little bit later in the evening, it would actually give me about 115% of the analyte. So we had to go back once I had all of this information and literally the way that the problems are going to be set up in the exam is I will come out and say a concentration of, let's say, 2 ppb or more is toxic. And let's say run position 2, the reported concentration of that sample was, say, 1.7 ppb. So the instruments tell me that the concentration of this really toxic chemical that I'm dealing with, most of the time it was PCBs and dioxins and stuff like that. And go ahead and look up PCB and dioxin toxicity. Some dioxins are highly toxic, but it was reported to be 1.7 ppb. If we know that for this particular chemical, anything 2 ppb and above should be reported, and the land that this sample came from, or the waterway that this sample came from, should actually be reported and potentially remediated in order to remove the toxin from it. However, if the amount of toxin is below that level, basically what's going to happen is what? It's going to, it's below the level. So in this case, unfortunately, we're not actually going to do anything to remove that toxin because it's considered, say, at a safe level. So I'll say down here 0 ppb to say 1.99 ppb. It's going to be considered safe. So if you look at the concentration that the instrument said is in there, I get 1.7. 1.7 falls in this safe range. So even though it is a little bit higher on the scale, when I'm reporting back to my manager or my department head or anything like that, the value that I report back is going to be that 1.7. But I also know that that 1.7 is also going to be 76% of the total of the actual total. So how do you take that into account to make a correction to the value that we've got down here? And this is a formula that actually will be on the exam, so you don't need to memorize any of this. But literally what we were doing is, so early in the morning, the result came back as 1.7 ppb. And if I report that, it's considered safe. If it's considered safe, the company that owns the land or owns the river or whatever doesn't have to spend a lot of money to fix it up. But we also know that it's 76% of the total. So what ends up happening is we use a formula, or I used a formula to say reported concentration is equal to the percent reported, or the percent up here, times the actual concentration. Using the numbers that we have, this is going to be 1.7. This is going to be equal to 76%, but I have to put it in as 0.76, and then actual is going to be this x. How do I get the x all by itself? X is actually going to be 1.7 divided by 0.76. And if, of course, I got rid of my calculator on the screen, but we can use a calculator on my phone. Hopefully we can see what's going on. So 1.7 divided by 0.76. This is telling me that the actual concentration of the sample based on the instrument and my everything that I've got here is actually going to be 2.24. So originally the instrument said it's 1.7. That puts it in the safe range. When I go back and try to correct the concentration based on uh, issues that I know the instrument has, the actual concentration that I get is now 2.2, which means that particular sample is probably actually toxic. And if this is a soil of somewhere, that would mean that the company that owns this land now needs to go out and perform remediation on the soil. That remediation can cost millions of dollars. Um, if the company doesn't do it, basically they are poisoning anyone that walks and goes around on that particular plot of land, which could help or hold, or they could be held liable later on for, uh, say, whatever type of medical condition happens because of that. Now, let's say I've got another sample here and it came out. So again, using the calculated or the calculation, or sorry, using this idea of reported concentration is equal to some percentage times the actual. Let's say later in the day, my reported concentration is 2.4 ppb. Oops, sorry. Uh, so again, 2.4, that puts it in the toxic range. So I would report that to my boss or my department head and say on this sample, we got 2.4. Uh, they know that anything above 2.0 is toxic. So it's looking like whatever this sample is actually needs to be remediated. But if we know that the reported value is 130% of what it should be, again, for the percentage here, I have to make that a decimal value time or 1.3 times the actual value gives me the reported value here. How do I get the actual value? That's going to be that 2.4 divided by 1.3. Now, if I do that with my calculator, uh, so 2.4 divided by 1.3. And in this case, the actual concentration comes out to be 1.85 ppb. So what's happening here is this is safe. Is it elevated? Definitely. But it's considered in the safe region because we're, as I said up here, anything between 0 and 2 is considered safe, and above 2 is considered toxic. So if these are two different clients, this client right here gets to remediate, and which means that they spend all sorts of money, but they don't have to. For this client up here, uh, if we just use the value that we got, which is what we're actually supposed to do, this client is told that they are fine, but it ends up being that they are actually in a toxic range, which means that the whatever the company is that hired our company to do these analyses, they should be spending the money, but they're not. In both of those cases, uh, one of the things that can actually happen later on is when someone finds out that, say, the site that was considered toxic was actually fine. Uh, where did the information come from? Well, it came from the company that I worked at, which means that the company that I worked at is liable for any mistakes that we made. And the company that I worked at can actually get sued, and it did, and lost because it should have, because it told one of its clients to spend money it didn't need to. Uh, Cleaning up or remediating the site that this these toxins were at. Did that make the site a lot better for, say, the people around it? Yes, it did. So, did the remediation actually do some good for the, say, the local community there? Yes, it did. But just because of the way regulations are set up, because of the way companies behave and stuff like that, the company is looking at it and saying, hey, we spent a whole lot of money we didn't need to. Let's recoup a lot of that money from the company that gave us this misinformation. Uh, So they got sued. With the other sample where the concentration according to our instrument was below, but when we do our correction calculation here, it actually comes out as being above. Well, someone else came in, tested that the same site, and they found that everything on that site was actually elevated, but the company that was working on the land and all of that didn't do anything about it. So what happens? The company got sued for not remediating based on the recommendation and based on the testing of the company that I worked at, which means the company that I worked at got sued again. Anybody want to guess whether or not they're still around? And with all of that, this is actually stuff where I complained bitterly to the quality manager. And quite literally, the quality manager told me to shut up and I didn't know what I was talking about. Uh, Meanwhile, or at that time, I'd only taken 5 or 6 stat classes. He had never taken a single one, but he thought that he was better at statistics than I was, and it cost the company that he worked at. So sometimes these mistakes can be costly. Sometimes these mistakes can be deadly. In the case of what we're looking at here, talking about reproducible results, how reliable are the results? How repeatable are the results? Well, with the instrument that we were using, uh, the results were actually very repeatable. As long as I always ran it in the morning, it would always come up below that threshold. If I always ran it in the evening, it would always come above that threshold. But uh, even though it's the same sample, just be since the instrument was not working right, that's the reason why it was going on. And one of the things that I actually did is, again, getting back to, say, the difference between a t-test versus a multiple regression model like I did, or like we're going to be doing next week. I took six, 6 or 8 vials. I think it was 8 vials of the standard that I was using. And on the files, I just put A, because why not? On the other 8, I put B. And then I ran every single one of those samples, A, in a row, then B, 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 B. The liquid that was inside of them was exactly the same. But when you go and you look at the average of the A versus the average of the average of the B was statistically significantly higher. So getting back to the some of the ideas that we have to have with t-tests, normally distributed, was the data normally distributed? Yes, it was. Were the samples that I was running representative of the population? Yes, yes, it was. Uh, what between group A and group B, was there only one change? No. Uh, the label that I put on there, A versus B, was complete bogus. And I knew it was complete bogus. But for giving it to the quality control manager and saying, well, my group A standards are quite a bit lower in concentration than my group B standards. And he went off on how I was incompetent, didn't know what I was doing, and I needed to be able to make my standards a whole lot better. And then I told him essentially all my standards, and I don't have any glassware, but it was like basically everything came out of here. The only difference between A and B, A ran first, B ran second. So there were actually two different things going on. The confounder was how was it run earlier in the day versus later in the day. When I ran them A, B, A, B, A, B, A, B, all of a sudden the exact same samples no longer showed any difference between them. And I think like 2 days later, I was fired. But you know what? I didn't work. I didn't like working there. And uh, if it would actually be, say, potentially my butt on the line, if I was the one who, say, was the uh, chemical technician of record when these samples got the company sued. So I'd be more than happy to be unemployed and not get sued for millions of dollars than to be employed at this place working for these people and basically get sued for millions of dollars and be legally or held legally liable for the incompetence of my manager and the incompetence of the quality control manager and department head and all that. As so, anyway, I'll let you all go for the rest of the evening. We'll pick up a lot of this next week, and I will hopefully have a lab that you can all work on using SPSS as well. So, torch you all later, even more than so than I already have. See ya.